Introduce today's speaker. Cheng-Lin received his master's degree from the Department of Physics in in National Taiwan University under the supervision of Professor Sheng. After that, he went to the NTU IBM Quantum Computer Center as a research assistant, and now he is a research assistant in Professor Zheng Haozhong's group. His research interest is the quantum chemistry and the quantum machine learning. And let's welcome Cheng-Lin.
Can everyone see my screen?
Yeah.
Okay, thank you for the kind introduction. Hello, everyone. And I also want to thank the Hong Hai Quantum Group for giving me the opportunity to talk about our work. This work is in collaboration with the City University of Hong Kong and the University of Maryland. You can refer to this general reference if you want to know more details. Okay, let's start it. Here is the outline of my today's talk. I will briefly, let me open the pointer first. I will briefly review quantum chemistry first and illustrate why quantum chemistry calculation is considered one of the most compelling applications for quantum computing. After reviewing basic quantum chemistry, I will connect quantum computing and quantum chemistry and discuss the current application and limitation. Later, we will move on to our motivations and the model, and I will show you our results under different settings, the noiseless setting and noisy environment. And finally, I'll make a conclusion about this work and what we can do better. Okay. Now, let's take a brief review of quantum chemistry. Look at this picture here. In quantum chemistry, we can dive into this two-dimensional picture. The x-axis is the number of basis functions, and the y-axis is the method path, or mean number of configurations. There is a hierarchy for initial method, with most basic approach to many electron systems being a Hartree-Fock method. In this approach, only the exchange of electrons is accounted. The Hartree-Fock method neglects how electrons interact through correlation. And as such, the total energy from a Hartree-Fock calculation do not contain contribution from this effect. That is, no correlation energy. So, improving the electron correlation problem has led to theoretically developing more useful treatment, starting from the point of this point, the Hartree-Fock calculation. Because they start from the Hartree-Fock calculation, we call this method is the post-Hartree-Fock method. And we want to get more correlation energy. And the correlation energy is defined by the exact answer minus to the Hartree-Fock energy. So in the ideal world, the complete approach accounting for electron correlation is the full configuration interaction, which denotes full CI here. It is highly accurate, but extremely expensive. But we can use quantum computer to solve this problem. That's why we can make a connection between a quantum chemistry to a quantum computing. However, not only can accurate total energy for a chemical system by obtaining through the electron correlation method, the y-axis, but we can increasing accurate total energy by using larger basis sets. What is basis set? Basis sets are sets of functions designed to represent the wave functions of electron density. With larger basis sets, we can allow more flexibility and hence more accurate results, but a higher computational cost. So let's introduce the minimal number of basis functions, the minimal basis set. The essential idea of the minimal basis set is that we select one basis function for every atomic orbital that is required to describe the free atom. Take hydrogen, for example. Minimal basis function for hydrogen is 1s, just 1s orbital. For the second column, lithium, carbon, and oxygen, it consists of 1s orbital, a 2s orbital, and a 3 2p orbital. But we know that the minimal basis function cannot get the minimal basis set cannot get the accurate result. Let's see this Hartree Fock and excitation picture. Now here we change the x-axis and y-axis. In the x-axis means the level of theory. We can incorporate the more excitation or more scatter determinant into our method, and later we can go through the full configuration integration. But the basis set size, the number of orbitals, determines the quality of your Hamiltonian. So let's see the typical flowchart of quantum computational chemistry. We need to define the target problem from classical ab initio tools to generate the corresponding modular Hamiltonian and map the problem to the quantum computer. Again, this picture again. In addition to quantum algorithm, the choice of basis set is also of prime importance in quantum chemistry. So we can dive in this red box and blue box. The red box means the quantum algorithm or the method part. The quantum computer can only achieve this direction. But to get the exact answer or more accurate answer, we still need to consider this direction, the basis set. Since the choice of a basis set determines the quality of construct Hamiltonian, in quantum computational chemistry, we should balance these two things. Okay, let's talk about previous study for quantum chemistry. In this slide, you can see that most previous studies focus on the Gaussian type with basis. And if you look in the paper, you can see most of them use the STO3G, the minimal basis set. So it's easy to know they can't generate a good result, although we have a good quantum computer. Now, to talk about basis set, we have two main classes of a basis set. One is the plane wave. The other is the Gaussian. A plane wave is localized in Fourier space. Since it's localized in Fourier space, so it's easier to convergence. Also, it's an orthogonal function. The orthogonal function can help us easier to compute the overlap matrix, and is suitable for periodic systems. However, it's not adaptive. That is, the main problem of a plane wave is it's not adapting using the same resolution everywhere in the box, even where there are no electrons. So we need to use more resource to describe the no electron part. Look at the Gaussian or scatter type orbital here. It localized in real space, but it constructs from the non-orthogonal functions. And this will cause if we need to calculate the overlap matrix of Hamiltonian, so need more computational cost. And it's suitable for molecules, but it exists basis set superposition error. That is, maybe when in larger basis set, we can't get the better result. Also, they are non-systematic. So it's naturally to act. Also, they suffer the same challenge: more accurate, more functions, and need more qubits. So
sorry. May I ask a question?
Okay.
Can you explain more about the superposition error? It comes from the basis set the nature of the basis set?
Yeah. It comes from the nature of the basis set. Typically it comes from the Gaussian type orbital, but Gaussian type orbital or Slater type orbital is most of the chemistry used to describe the molecular system.
But when you talk about error, it is related to the device, right? Or
no. Let me. Okay, let's see this picture again. To get the exact answer, the full Schrodinger equation solution, we have the method, the y direction, and the basis function, the x direction. No matter your if you give you the infinite power of a computer, you can always calculate the full full configuration interaction to get that the given basis set the exact answer. But since we need to use no basis function to describe the electron density, but increasing the basis function not guaranteed, not always guaranteed. Use typically Gaussian type orbital, not guaranteed we can increase the final property. So maybe this is called a basis set superposition error. So okay.
So it means it may not be a good basis.
Yeah. Sometimes it may not be good basis. So if you want to do chemistry calculations, you need to learn more experience to choose the suitable basis function or to choose the suitable basis set. And choosing the basis set, you can determine what you want, such algorithm you want to calculate the corresponding energy in different levels. But basis set limited the final result.
Okay, I see.
Yeah.
Okay, thank you.
So is that clear? Is it another choice? Yes. The answer, we have the wavelet. In wavelet theory, there are two fundamental functions, a scaling function, phi, and a wavelet function, psi. You can show mark there. Also, the advantage of Daubechies wavelets are as follows. First, they are localized in both real and Fourier space. That's why we can see it adapt the two of the plane wave and Gaussian. It localized both in Fourier space and real space. So it's easy to convergence and have the atomic like orbital property. Also, it is orthogonal. So to calculate the overlapping matrix, it's more easier to calculate overlap matrix. And most importantly, it has a low activity, or we call a multi-resolution. What is multi-resolution? Take the water molecule here, for example. Near the atom, the blue part, we can use the high-resolution 3 points, carry both scaling function and wavelet function. So use the 8 degree of freedom to describe the more dense electron density part. For the far regions, we only use the scalar function to describe the part. And very far from away, we can since the density is 0, so there is no degree of freedom. Compared to the plane wave since is not non-adaptive. So for the 0 density region, it also needs lots of plane wave to describe that region, but wavelet not. Okay. Let's see. With this property, the wave function can be stored in a compressed form, and the final molecular orbital basis function can be expressed as equation 5 here, where S and D are the expansion coefficients. Now, we construct our Hamiltonian by using the same number of basis functions as STO3G. That is, for hydrogen, we only consider 1s. And if you spin a 1s orbital to spin orbital, spin up and spin down, it only describes 2 qubits. And with the limitation of qubit resource to describe the more accurate result. This set of minimal basis Daubechies wavelet molecular orbital is constructed in a much larger silver space, spanned by a grid of Daubechies wavelet functions, and also adapt to the structure of the molecule in the Hartree-Fock self-consistent field calculation. This one slide overview the main program will run. Since the grid spacing determines the accuracy of the above construction, with the suitable convergence grid parameter, we can treat the kinetic matrix analytically. Also, additionally, unlike calculation with Gaussian type orbital, our calculation treats the core electrons of given Hamiltonian using pseudo potential. With the pseudo potential help, we can describe the core potential more efficiently. And now we have the better second quantized Hamiltonian to run with the quantum computer. I think everyone familiar with the variational quantum eigensolver here. So this is just one page introduction. If the goal is to find the lowest eigenvalue of a given Hermitian matrix, and it has a one core concept of as quantum chemistry. It's based on the variation principle. And two components is an hybrid quantum classical. It leverages both quantum and classical parts to solve problems. And three states: unsolved repression, optimization, and measurement. In this work, the quantum computation part of DQE, we can see for the encoding molecular Hamiltonian to cubic Hamiltonian, we choose the parity encoding. By rearrange the orbital number, and do encoding, we can reduce the qubit resource from n orbital to n-2 orbital. That is, we only use the n-2 qubits. A few DQE ansatz for this work can divide in two parts. For the noiseless part, we use the chemical inspired UCCSD. That is, we want to guarantee for the good basis set, we can use by using the good method, we can predict good results. And later, for the noisy environment, we use the low depth curiosity ansatz. We want to answer if we claim we have a better input Hamiltonian, can this Hamiltonian be computed under the effect of noise? After that, we use the zero noise extrapolation to mitigate our results to get a better result. Now, let's come to the result part. The performance of the minimal basis Daubechies wavelet molecular orbitals. We first investigate the optimized molecular structure, bond length, at a vibrational frequency omega here. Calculate with quantum computer for small systems, including hydrogen, lithium hydride, and beryllium hydride. Why we choose the bond length and vibrational frequency? Since these two quantities are experimentally measurable, so we can compare to the experiment result. Here, let's look at the number of total spin orbitals first. Since the required number of qubits is generally less of the spin orbitals. To make a clear compression, we also run an exact diagonalization with the largest basis set, avoidable basis set, CCPPTZ. We use the 55 orbital for hydrogen. That is, to calculate hydrogen more accurate, you need to 56 qubits, and 86 for lithium hydride, and 114 for beryllium hydride. Due to the simplicity, we can let's look at the hydrogen molecule first. due to the simplicity of the hydrogen molecule, we can see that all methods include spo3G, give a reasonable bond length compared to experimental results. However, the vibrational frequency shows significant basis set and computational method dependence. We can see that the spo3G calculate the vibrational frequency is the largest error compared to the experimental result. And the Daubechies wavelet with the quantum computing, only we can reduce the error, the calculation error more than 10%. For the lithium and barium hydride, we can see that the Daubechies wavelet and CCPV-DZ and CCPV-TZ yield a bond length structure agree with the experimental value. Daubechies, let me change to another. Oops. This one. Daubechies wavelet and CCPV series, we can get a reasonable result compared to the experimental value. But now let's take the number of orbitals here. The number of spin orbitals used in Daubechies wavelet calculation is significantly less than the other, compared to 63 qubits or 36 qubits and 86 qubits, less than use the CCPV-DZ and CCPV-TZ calculation. This table shows that quantum computing cannot compensate for the deficiency inherent from the low quality basis set. That is, although given you a full power of quantum computer, you can do a very good method, a very powerful quantum algorithm to run the quantum chemical simulation. But if you have the bad basis set, the result you provide is bad, since the basis set determines the final result of your algorithm. We want to note that here we also compare to the CCPV-DZ star here. What is the CCPV star DZ star here? That is, we limited the bigger basis set CCPV-DZ to the same number of orbitals of the minimal basis. Consider, let us see the previous slide. The larger basis set consider more orbitals. The CCPV-DZ star is that we can limit it to some part of active space as the limit as the minimal basis set. And we can see that sometimes they can provide a better result for the hydrogen, for lithium hydride, and for the but not for the barium hydride. And here's the problem. Since if we can construct Hamiltonian from the larger basis set and truncate to the small active space, we can provide the same qubit resource and to predict the better result. But in this barium hydride problem, we can see that we cannot calculate its vibrational frequency, since near the balance structure, the answer is non-smooth, so we cannot calculate the vibrational frequency. And since we cannot calculate the vibrational frequency, we cannot guarantee that for the unknown molecule with the least procedure, we can predict the good property of the unknown molecule. Okay, here are the potential energy curve and corresponding errors for molecular hydrogen and lithium hydride. The right panel, the error is defined as the absolute energy difference with respect to the ground state energy value from the exact diagonalization in the largest affordable Gaussian basis set. That is, we use this CCPV-TZ as our reference, and we compute the relative errors with this reference. We can see that for hydrogen and lithium hydride, the DW wavelet type orbital, the blue line, is better than, is roughly same as the purple line in this part, and is always better than the truncate part, CCPVDZ limited active space. And for lithium hydride, the more complex molecule, the result is more significant to show that our Daubechies wavelet can generate a better result. And for the beryllium hydride, we can see that white is the non-smooth part. If we see that the blue curve, the truncate the CCPVDZ for CI. Near this, if we zoom in this region, we can here's the non-smooth property. So we can calculate from the balance point that we can calculate the vibrational frequency from the balance point. But for the Daubechies wavelet, it's so much smoother than the other approach, and keep the resource minima and get better results. Now, let's consider another molecule, the more important one, the water molecule. Why consider water molecule? Since this is a larger molecule with nonlinear geometry, therefore it represents a more complex text for the computational method. We know that the HOH bond angle is roughly 105.5 degrees. But if we scan the potential energy surface of OH bond length and HOH bond angle of STO3G, we can see that the STO3G result is unrealistic. The bond angle is smaller than 100 degrees, or almost less unrealistic. In contrast, the use of the minima basis Daubechies wavelet molecule orbital provides significant improvement in predicted bond length and bond angle when compared to the experimental value. And with the prediction of the prediction of the larger basis set, consider the CCPVDZ 846 4CI method here. We can get a better description on hybridization of the water molecule. Note that here the CCPVDZ 812, the truncate active space method, yield better results in bond length and bond angle than 4CI results. Consider, since these basis sets are almost the same, just like CCPVDZ 4CI is considered full of configuration, and CCPVDZ 812 is the limited active space. We consider only part of the active space, but we can see that this result is better description on bond angle than this result. This indicating that there exists the possible errors canceling that make a good agreement in restrict active space case. So how to choose a restrict? But we cannot always choose the right active space to do calculations. So the Daubechies wavelet molecule orbital construct from large real space grid of the wavelet function can better capture orbital angular dependence property. So we can get a better, more accurate water bond angle result, yielding a better Hartree-Fock wave function and for consistent results, and has a provide us a better Hamiltonian to adapt to fixable molecular structure. Now, we have seen the effect of more accurate Hamiltonian in a noiseless environment. It's natural to ask how it performs under the noise effect. Here, I show here. In 2019, the IBM team used hardware-efficient answer with error mitigation methods on hydrogen and lithium hydride. We can see from this point, they can achieve more accurate results by scaling the noise level. However, if we look close, the arrow part here, it does not achieve chemical accuracy. The chemical accuracy here roughly 10 to the -3 Hartree. So you can see most of their points cannot achieve chemical accuracy. Here, we intend to compare our results with that previous study. So we perform quantum simulation using Saturn quantized Hamiltonian based on the minima Daubechies wavelet molecular orbital for lithium and hydrogen for hydrogen and lithium hydride. The numerical experiment used the low depth series ansatz for these two molecules, just very low depth, just depth 3 and both depth 3 to description. In the right panel, figure 5 shows the potential energy curves of the PQE simulation for hydrogen and lithium hydride using the DW Hamiltonian construct on the minima basis. First, we can see that the raw data of Wavelet can run in achieve the chemical accuracy and need not to any error mitigations. This result from the and we see the lithium hydride. Here, the BND is for lithium hydride. After run the error mitigation, the red point, we can see that our lithium hydride simulation under the noise effect also can achieve the most of point can achieve the chemical accuracy. And also we rerun the STO3G simulation. The result from the STO3G basis set and respective classical calculation are also present. And we can see that STO3G raw data is very bad. But after mitigation, they sometimes can achieve the chemical accuracy, but lots of points, like the previous result, cannot achieve the chemical accuracy. So here is the conclusion. But before the conclusion, I'd like to recap its picture. We know that we should always remember that for quantum computational chemistry, there are two directions. If we consider a quantum algorithm or in PQE simulation, the ansatz for quantum chemistry need not to cover a whole Hilbert space. We can always find the possible configuration with the low depth, but this is always the y-axis direction. But more importantly, in the next area, the quantum chemistry simulation need to consider quantum algorithm and incorporate an appropriate basis set. That is, we cannot always use STO3G and to design the quantum algorithm. We need to consider the more accurate Hamiltonian things. Increasing to for typical molecular orbital, if we use the Gaussian basis set to increase the discretion, you need to add the more basis function, and it needs more qubit. consider in a niche area, the qubit resource also an important. So how to choose the low-wise Hamiltonian, also an important part. And our Daubechies wavelet basis improve the quality of Hamiltonian while keeping the quantum resource minimal. That is, if we can ignore the y direction, the quantum algorithm part, we can use the same number of minima same number of basis function as STO3G, the minima basis. And our choice is a better discretion, more than maybe 631G here. And after that, we can adapt any quantum algorithm we like to calculate the final result. So in this work, we demonstrate that the minima basis set constructed from Daubechies wavelet functions for quantum computer can yield accurate results in agreement with experimental data. Also, we indicate the importance of the choice of basis set in applying quantum computing to quantum chemistry. Still, the Daubechies wavelet it bridges the grid method and adopting both orbital basis set methods for quantum computation and quantum chemistry. And it's easy to see the outlook. Since it adapts from the classical chemical aesthetic, so the conventional approach to reduce the size of active space can also directly applicable to this Daubechies wavelet basis method. Also, as I said before, the y direction, the method part, we can after choosing the better Hamiltonian, we can also use different encoding scheme and quantum algorithm with the Daubechies wavelet basis. Okay, here is the end of my talk. So if you have any question, feel free to ask me.
Is there any question from the audience?
I may have some questions. Can you go back to your next slide?
Okay. Let me. Am I sure it's screen off? Slide.
Okay. You mentioned you can try different encoding method, right?
Yeah. So maybe let's from this slide. That is the more important part of this work is focused on the blue region. That is, we prepare the better classical preparation for molecular Hamiltonian. But for the red region, the quantum part, we also need to map the molecular Hamiltonian to qubit Hamiltonian. So even we choose the better molecular Hamiltonian, we can reducing the qubit resource from the mapping part and choosing the good quantum algorithm part to implement to solving our qubit Hamiltonian.
You mean when you have chosen your method and basis, you also need to see how to convert into qubit Hamiltonian?
Yeah. That is the blue region. After choosing that, you determine the final quality of your Hamiltonian, or we can see that the upper bound of the Hamiltonian. And but by choosing the method, you can always reduce choosing the build like for CQE, you can use the chemical inspire or some machine learning answers, something like the quantum architecture search to search the efficient answers for variational quantum eigensolver. and after that we can get the better answer. But the limitation of the answer is bound by the choosing of basis set. So to do so to do the quantum computational chemistry, we cannot only focus for the red part. Since if we always do this direction, what I need to do with quantum computer? Since STO3G is very although we can do it with quantum computer, since 4CI is very expensive, but STO3G or the minima or other basis, STO3G is not cannot predict the correct chemical property. Although you have the full power of the quantum computer, so we also need to consider the x direction, the number of basis functions, and incorporate these two thoughts to the all quantum computational chemistry.
Yeah, I understand. But my question is, you mentioned several times of low depth circuit. So,
yeah. Oh,
so
okay.
the low depth circuit, it is depending on the converting to cubic Hamiltonian, the choice of what's the dependence?
Yeah. But maybe I forget to mention. Since now we can get the better description of Hamiltonian. So for the quantum chemistry, what we want to get the correlation energy, the exact minus the Hartree-Fock. So if we can provide the better description on Hartree-Fock, the correlation energy we need to solve is very small. So we have the very good starting point. That is maybe the exact answer here. Maybe after the choosing, we can start from here. So the correlation energy need to solve is very small. And also from this circuit, if we run this circuit for STO3G, you can see that sometimes for STO3G for other more complex molecules, maybe it cannot convert to the better result, but Daubechies wavelet can. Since in the Hartree-Fock level, it provides a more accurate result than other bases. So for the quantum considerations, we only use the law circuit to get that correlation part. Yeah.
Oh, sorry. What do you mean more accurate in the Hartree-Fock level? You mean for different basis set, or for which different case? You can have better Hartree-Fock level accuracy.
Can you say that question again?
I'm just wondering how can you have better Hartree-Fock result? I didn't get the point. It's because of the choice of basis or what?
Yeah. So it is also it thinks Hartree-Fock is the number of computation. It belongs to the method part. And what is the I think in 2021, the Google team do the Hartree-Fock limit. That calculate the Hartree-Fock method for the larger basis set by using quantum computer. But this Hartree-Fock limit didn't have any correlation. What is the better Hartree-Fock? That is, since if we use the minimum number of basis functions, but if we use the traditional Gaussian type orbital, we can only get this result. But since the Daubechies wavelet is constructed from a grid point, the real space, so we cover the full Hilbert space contained in that grid point. So maybe our starting point is it's like here. So I would say this is a better Hartree-Fock, or the better Hartree-Fock, but we can keep the number of basis functions smaller.
Do you have a intuitive explanation why the better choice of basis set can be more accurate
Oh yeah,
Because,
let's since I said the basis function determine the discretion on electron density. If you consider this, for the STO3G, we only describe the core orbital, 1s orbital. But for the 631G, we incorporate the 2s orbital. Although we know that the hydrogen atoms, the electron is common in the 1s orbital. But for the larger basis set, we will incorporate the other basis function coming to the atom. So the more discretion on the atom's wave function, so the more accurate its property it has. But increasing the basis is roughly increasing the basis is equal to increasing the basis function. But increasing the basis function is equally to increasing the number of qubits. So if you want to, although you can get a full configuration, but I think the quantum computer is very powerful in the gate era. That is, we can do the very long. we can get we can achieve very long depth circuit. But if the limitation or the quantum resource, I say the qubit is limited. That is, if I give you the 10 powerful O2O connections, number of qubits, you only can do the 10 number of qubit things. That is, maybe you can solve the 10 number of orbitals, something only like the, I think, oxygen atom, oxygen. But the more other you can't. Things you can see in this table. If we see other element, chemistry element, if we need to describe it more accurate, we need to increase the basis function, and the basis function is roughly equal to the number of qubits you need to use for encoding the Hamiltonian.
yeah, I see. Sorry, but I may still miss about the depth and the qubit number. So that's the less qubit means low depth, or what's the?
No. I would say less qubit. I would say the low width, the low width. That is typically the research article maybe will focus on the quantum algorithm. They want to calculate the low depth thing. The low depth thing, that is the good quantum algorithm for quantum chemistry to get a better result, something like the quantum-based estimation, but it's not applied for this area. But we want to point out that no matter you can how good this direction to get the exact answer, you need to consider this direction. But consider this direction. Typically increasing the basis function, you need to increasing the number of qubits and increasing the circuit width. But by using this approach, we construct a better Hamiltonian in minimal basis function. We can use the low width function. And with low depth circuit, due to the this area limit, we can also get a better result against the experimental data.
Okay, I see. So the more complicated method will increase the depth, but you keep the method simple by choosing appropriate basis, which means low depth, low width. Yeah. Okay.
Yeah.
I see. So, sorry. More question about some errors you present in the simulation results. So in the some error part, what's the reason for those? It's because the great wave function wavelet cannot capture the accurate wave function, or what's the source of the error?
Yeah. That is another question. So that's why we first focus on the traditional chemical inspired wave function. Since typically the couple cluster UCSD unitary couple cluster single and double excitations can capture the most of the correlation ends of the can get the most of correlation energy, and the wave function it provides is more accurate to solve for this molecule. But in the noise effect, we want to compare to the previous real study. Why? Since in this area, we can't to implement the unitary couple cluster beyond a hydrogen molecule. So you can see lots of the experimental, they always do the hydrogen or 4 hydrogen or 10 hydrogen. But for large molecules, some lithium hydride or water molecule, they cannot done. It seems it limit to the number. It cannot done since it limit to the number this area technology. And so to make a comparison, since the previous IBM team also used the heuristic ansatz, we use the heuristic ansatz as then used. So to do a fair comparison between the results. But for the theoretical guarantee, we simulate the results under the UCCSD simulation. The noise effect, it just want to show that this molecular Hamiltonian is suitable in this area.
So you mean you get inspired by more accurate classical method like couple cluster, and then
yeah.
So how's the conversion from couple cluster to the wavelet you choose? So you mean you expand the couple cluster wave function by those wavelet or by what method to do the conversion?
Maybe let's restate. The couple cluster or the method part follow from the y direction. The wavelet is provide the blue part the x direction. We provide a good starting point, and after that we can more good starting point under the same basis function can provide a good starting point. So, but the unitary couple cluster is the method for the PQE implementation. It's the answer choice, and almost the unitary couple cluster is directly inherent from the classically CCSD method. So for this molecule, unitary couple cluster is guaranteed to provide the most roughly exact result as the full configuration interaction. That is, the unitary couple cluster can provide near to exact diagonalization. So you use the unitary couple cluster to demonstrate our Daubechies wavelet method can achieve the same achieve the better accuracy by using the same number of orbitals. So that's we say maybe this convergency.
Oh, I see. So sorry, I get confused. So you mean the couple cluster is the direction of method?
Yeah.
This
is the direction of this here is the direction of basis and the direction of method. Why we compare unitary couple cluster to a full configuration interaction is for this molecule, these two methods is roughly the same result.
So if you use the same, basically say in principle, if you use the full CI, it can be better, right? Or
But why we need to content computer things for the complex molecule, if we want to do a full CI, we need to incorporate all excitation. But this is the exponential scaling. But since the quantum computer can provide it has a superposition and entanglement property, so it's more easily to provide the better starting better wave function. That is possible to provide a superposition wave function for for initialization. But for classical, it's very hard to implement to cover all these parts. It's suffer from the label theory suffer from exponential scaling. Yeah.
So you mean you cannot incorporate more label or for what reason? I didn't get the point.
Oh, that is for the here is the math basis set and method part. We always can use the basis the given basis set to do a dual configuration interaction. But why we not choose the full configuration interaction, since if for the complex molecule to do the full configuration, to do a full CI calculation, it needs the exponential cost. But compared to the but for this calculation, the UCCSD can roughly generate the same result as for CI. And UCCSD is easily to implement on quantum computer compared to the classical implementation for CI.
Okay, I see. Thank you. So what's the future direction you think may be doable for in this field?
In this field, since we indicate the importance of the choosing of basis set. So here are some of paper or research direction focused on how to choose the suitable active space selection. That is, as I mentioned here, since we compare also the truncative, you can see here also CCPVDZ, but we truncate the total number of spin orbitals from 46 to 12. But it sometimes can get a better result, but sometimes it can't get a better result. The active space selection is also a study for quantum chemistry. But here now I have seen some from quantum information theory point of view. They calculate the orbital correlation first, and from this to select the more important orbital. And since we can select the more important orbital, we can select use this important orbital for quantum chemistry simulation. Also, the other direction is that since we have done all these parts, we have done all these blue region parts. But the more things is from molecular Hamiltonian to qubit Hamiltonian. Something like I think maybe my collaborator Xu has presented here before. We can concentrate a more physical configuration here to reduce the number of qubits while mapping. Also, we can focus on the quantum algorithm part. Since this blue part is determine the final quality of your answer, but the quantum part blue part is about the qubit resource, the qubit wise, the circuit wise. But the red part, the y-x directions, if you focus on this direction, you can the main topic is how to use the low depth circuit to do the low wise computation.
Yeah, I see. So when you mentioned the correlation from quantum information, you mean you do the calculation before putting into the real simulation?
Yeah. That is from this blue part. Here also can input some quantum information theory technique. Since orbital and orbital they have the classical relation and quantum relation. We can dive into which two orbital is the more correlation and more important, and use them to select and put into our molecular Hamiltonian and map into a qubit Hamiltonian. Yeah. So the classical part can also apply the quantum information toolbox. Yeah.
Okay. Sorry. So it looks to me the choice of basis is case dependent, right? So are you mentioning some direction is to do the systematic choice of the basis function as you mentioned in the first part of the direction, or I misunderstand?
Yeah. Maybe some for since we cannot determine the general basis for the unknown molecule, but typically if you choose the larger basis function, it can provide the more accurate result. It can always provide a more accurate result. So I think for the DFT simulation, when they want to design the DFT method, they always choose the like something like the large purple basis. Maybe for the hydrogen, you need to the 20 or 30 more orbital to describe, or just only one hydrogen. So for the large molecule, you need more basic function to describe. But if we want to focus on the quantum simulation problem, since the chemical problems also has some systematic effect, so you can choose the one series of the molecule, something like hydrogen, and for the maybe at least for example, we can change the lithium to any element of the second group. Yeah, you can change, and I think since they have the same property, so maybe you can use the same technique, and from this direction, the basis I choose is not depend on the can have some systematic point.
Okay, I see. So in the table, what's why D and E cannot be calculated?
Here, the experimental data for BH2 cannot be calculation is from the Raman light spectrum cannot detect for this mode, but for the other mode, since the BH2, let me go. Here is beryllium and hydrogen. They have two oscillating modes. This oscillating, same direction, and this same direction and opposite direction. But for the calculation of for scan the potential energy surface, we can only compute this one mode of the vibrational frequency. But this mode of vibrational frequency cannot be done from experiments. And for this D part, while this is the CCPVDZ star, the star means we limit it to the active space. So since we truncate the possible, maybe the original orbital will like I think for 46, but we only focus on the first 12. And since we only consider this first 12 orbital, when calculation the energy, some under the balance of band structure, they are non-smooth. So I say I put they are non-smooth potential energy curve in the region near optimize the bond length. So it can't. So that is, although this method also can reduce the qubit resource, but it cannot always guarantee you can calculate the experimental measurable property. But
So
Wavelet, yeah.
So you mean for the less orbit level, like the 12 here, sometimes it cannot just produce the smooth potential.
Yeah. So
And,
how to choose? But you can also say, but we can always select the more, or we can also to limit to the 12 orbital. But how to choose these 12 orbital is also a study. So that's why I say from the quantum information theory, sometimes they calculate the orbital entanglement to determine which orbital should be considered to put into this box and for calculation. But for general selection, you cannot always guarantee this can provide a better result. Especially for the hydrogen, you can see that, wow, for this truncate part, we can calculate the angle more accurate, more close to the experimental result. But if we incorporate the upper orbital into calculation, the result become not good. So the selection maybe need to consider and have the large effect for calculation. But this work we present, we can construct the same number of basis function. That is, use the minimal basis function to get a better result against the experimental data.
So all these are now related to the shoot-off potential, right? You just need the shoot-off potential as the input. All this has nothing to do with the shoot-off potential.
Yeah. The shoot-off potential part is another study. But since this code we implement by the big DFT, the big DFT want to make the all electron part. Since shoot-off potential want to incorporate they want to change. They want to incorporate the core potential, so they use the pseudo potential. The choice of pseudo potential may affect the final number, the final accuracy. But their team may want to make the all electron calculation. But we want to how can I say? Oh, but in this work, to reduce the pseudo potential effect for the larger molecule, such like the hydrogen, such like the water molecule, we have the Boson core approximation. That is, we Boson the core orbital, so the pseudo potential effect and the all electron core potential effect can be temporarily neglected. So we only cover from the upper orbital effect.
Okay, I see. Thank you. So maybe final question or comment. Do you try the spherical wavelet? It does because some molecule may not be suitable for rectangular wavelet.
Yeah. Then here are lots of wavelets to can use for the quantum chemistry calculations. Just the Daubechies wavelet thing is the most famous one. But yes, this is another point. We can always use the other wavelets to construct our molecular orbital, and this can be another study. Yeah, but I am not. I don't try this yet.
Okay. Thank you. Thank you very much. I'm done. Thank you.
Thanks.
Yeah, it's very good.
Is there any other questions? Okay, if no, I think it's about the time to close the talk. Yes, thank you, Cheng-Lin.
Thanks.